I hope you are able to do higher math because we're getting to numbers as high as 6 in this talk. Saving Math from Plato as a subtitle, A Randian Approach to the Foundations of Mathematics. Now, Randian is in scare quotes because it scares me to use that word. And I use it because I'm not sure that Ayn Rand would agree with this. There are certain formulations of certain points that seem to be disagreeing with what I'm saying. But on the other hand, I'm applying her basic ideas and many of her statements, as you'll see, because I quote them. So proceed at your own risk. Mathematics is in trouble. Not the content of mathematics, but the way mathematicians and philosophers think about mathematics and describe it to the public. Here's Bertrand Russell. Mathematics may be defined as a subject in which we never know what we are talking about, nor whether what we are saying is true. Now, bear in mind, mathematics is the symbol of the cognitive efficacy of the mind. Mathematics is the poster boy for logic and clarity and absolutism. It's something that, if it's shattered in the public mind, hurts the prestige of reason itself. Morris Klein, a very perceptive commentator who is a mathematician and has written many books on the subject of the history of mathematics and related topics, says the present state of mathematics is a mockery of the hitherto deep-rooted and widely reputed truth and logical perfection of mathematics. He says, the hope of finding objective, infallible laws and standards has faded. The age of reason is gone. Mathematics saying the age of reason is gone. Albert Einstein, familiar name? How can it be that mathematics, being after all a product of human thought, which is independent of experience, wait a minute. A product of human thought which is independent of experience, warning flag, is so admirably appropriate to the objects of reality. This is a big theme that's discussed in the philosophy of mathematics and by scientists and mathematicians. How come mathematics so aptly describes physical reality? It comes from another world, and yet it applies to this world. Here's why they think it, or how and why they think it comes from another world. Plato's system. There's a little table here to talk about the three things, perception, reason, and mathematics, as an example of reason. Each one I give the object and the status of the object. So perception for Plato is about the concretes of this world. Hey, we found something we can agree with Plato about. Perception is of the concretes of this world. And what is the status of perception? Well, the concretes are messy. They're semi-unreal. They're changing. And Heraclitus taught us that that which is changing is what it isn't and was what it wasn't and can't step in the same river twice. Plato talks in the parable or allegory of the cave about prisoners in the cave looking at shadows on the cave wall cast by a fire behind them. And they don't know what's going on, but they think they know what's going on because that's all they know. And that's the way the common folk, the people who cling to their religion and their guns, look at reality. They think it's real, but no, it's really not. Reason, on the other hand, Plato says, context, the higher world, the good world, the perfect world, the world that he describes as the really real reality. That's an actual translation of a Greek phrase that Plato uses for the world of forms. It's a world of perfect things like the perfect man and justice itself and beauty itself. Now then, mathematics sort of contacts the world of forms. There's a technical reason why it's sometimes placed as an intermediary, but it's really part of the world of forms. Mathematical objects are perfect and real, really real. So the circle of the mathematician described by algebra, which Plato didn't have, x squared plus y squared equals r squared. That's perfect. But the circles that we draw in this world are imperfect. And the question is, how come the perfect, the circle from the other world, the ideal circle, works in this world? Here's an entry from the Stanford Encyclopedia of Philosophy, a very authoritative source, in a good article. It's not that the article's advocating what I'm going to read, it's describing this as the problem that Aristotle faced. The physical straight lines we draw are not straight. A physical tangent line does not really touch a circle at a point. In other words, physical objects fail to have the mathematical properties we study. Look at Euclid to see this in geometry. Here's Euclid's first definition. A point is that which has no parts. A line is breadthless length. Sends a chill through me when a line is breadthless length. Those things don't exist, right? I mean, maybe atoms don't have parts, but he wasn't thinking of that. He was thinking of the mathematical point where two lines intersect, but they have no breadth. So it's kind of hard to understand how they could exist, let alone intersect. Pop quiz. What are the entities or objects that mathematics describes? A, objects in the world of forms. B, inhabitants of mathematics land. That's the implied view of many people. C, ideas in the human mind. D, elements abstracted out from perceptual concretes. None of the above. Did someone yell that out? None of the above, in my view. And we'll see why in the next section here. Let's pause to have a touch of reality so we can get back to why it's none of the above. What facts of reality? This is Ayn Rand's magic question. What facts of reality give rise to the need of such a thing as mathematics? Well, a friend of mine has a palm tree in front of his house. It's really tall. We were wondering, how tall is it? I mean, it's really tall. So there's a way that you can figure that out. If you measure the shadow of the palm tree, let's say it's 100 feet, and you call the height h of the palm tree. You got a little triangle there from the sun's rays being the diagonal hypotenuse, h being one leg of a right triangle, and 100 feet being the other. So if you set up a yardstick at the same time and measure its shadow, the proportion of the height to the shadow cast will be the same. So 3 is to 5 as that unknown h is to 100. And that's 60. So we determined the height was 60 feet. And was approximately that. I don't remember the actual numbers, but about 6 months later, a tree trimmer climbed up, and he had a way of measuring it. It was like 58. It was very close. So what facts of reality give rise to the need of such a thing as mathematics? Things like that. The need to acquire quantitative information. The need to acquire quantitative information, i.e. measurements, 60 feet. Mathematics, Ayn Rand describes as the science of measurement. But I think it's more accurately described as the science of inferring some measurements from other measurements, because it's not the science of, well, go out and lay a ruler down, or get yourself a tape measure, or use this instrument in this way and then put it down, move it along. That's not what mathematics does. It tells you if you've got a measurement of 3 feet to 5 feet, and it's the same as an unknown height to 100 feet, the answer is 60. That's mathematics. So I call it the science of calculation. You could call it measurement calculation if you want to stick real close to Ayn Rand's definition. It's a how-to science. Mathematics is a how-to science, how to calculate some measurements from others. Now here I can quote Ayn Rand. Mathematics is a science of method. The science of measurement, i.e. of establishing quantitative relationships. My view is that math is a tool. It is a tool for calculating measurements. It is not a description of anything. Sure, it involves some descriptions in passing, so to speak, like the Pythagorean theorem. The square in the hypotenuse is equal to the sum of the square of on the other two sides. But who would ever care about that if it weren't for using that when you know part of the information to get the other information, like we did in that proportional problem? I mean, suppose it's also true that the ellipse on the hypotenuse is equal to the area of the ellipse on something. Who would ever think to look for that? The only reason the Pythagorean theorem is developed is because it's immensely useful in working with things that have angles, forces, and everything in physics uses the Pythagorean theorem. Math does not describe things. It infers some measurements from others. So that's why I gave none of the above as the answer. What are the entities or objects that mathematics describes? It doesn't describe objects. It tells you how to interrelate measurements. And what is measurement? Well, Ayn Rand again tells us, measurement is the identification of a relationship. A quantitative relationship established by means of a standard that serves as a unit. And that's the part that we're going to have to dig deeper into, a quantitative relationship. It's very helpful to sort out what is quantity from other things like numbers. What is quantity? Well, it's an irreducible primary. It's like, what is an attribute? What is an action? Aristotle listed quantity in his categories of being. It's certainly an ultimate a genus in my scheme. You can't say, well, quantity is an attribute pertaining to quantity. I mean, it's rock bottom. Quantity is a quantity of something, so it's not rock bottom in that sense, but it's irreducible. It's a primary fact. Quantity is metaphysical. Numbers are epistemological. Quantity exists whether there are any human beings around or not. Numbers wouldn't. Quantities existed before the earth was formed, but numbers did not. And this is easy to get mistaken. Then there are numerals, which are linguistic things, which are the linguistic way that numbers are expressed. And I'm going to concretize it for you. Quantity is fact. It's metaphysical. For example, you have so many hands. Now, I'd like to say 2, but then I used a number. You have this many hands. That's a fact. Numbers are concepts. For example, the concept 2. Numerals are words. Zwei, symbol 2, Roman numeral 2, binary 1, 0. Numerals are the way that numbers are written or spoken. It's linguistic. Now, that doesn't mean they're dispensable, as we'll see. They're symbols, and we use symbols in math. Numbers measure quantity. Numbers are epistemological, measurement is epistemological, quantity is what's out there. How do numbers measure quantity? Well, unfortunately, there are 2 kinds of quantities, so we have to discuss them, how they're measured separately. There's multiplicity and there's magnitude. This distinction is like the distinction between pro-life and anti-life, or rights and a violation of rights, except they're both good things. Existence and consciousness. There's a big divide here between multiplicity and magnitude. Multiplicity is entities in a group. They're discrete items. How many of us, how many people are in the room? Multiple, many, a lot, maybe 100 and so. Magnitude is an attribute of one entity which varies, capable of varying continuously. For instance, multiplicity, the x's, there are 4 x's and 3 y's. That's one kind of quantity. Magnitude, the red line is longer than the green line. That's a difference in magnitude, amount of an attribute. Length, in this case, as opposed to the number of entities in a group. Pretty clear, and English picks up on it, although people violate it. You say there were few people in the room or little people in the room. Well, little people would be little people in the room, right? But people get this wrong sometimes with less and more and fewer, or they use the wrong word. But English does make the distinction between the discrete differences between few and many and the continuous attributes, intensity, variation, little or much. All right, so let's now turn to the first one. Let's measure multiplicity. Numbers measure quantity how? By a standard. That's not a shock. What is a standard, though? A standard, Ayn Rand says, is a concretely specified unit. We measure weight in pounds. We measure weight in weights. We measure length in inches or meters. Those are lengths. And the inch is a certain length. The meter is a certain length. The pound is a certain weight. We don't measure length in pounds. We measure every attribute by, well, that's really magnitude, come to think of it, by a version of itself, but we're going to apply that to multiplicity. So you're going to measure multiplicity by multiplicity. Here we are. It's a certain number of balls. I'm not going to give away how many there are, but we're going to measure them. One way is to find something that is a concretely specified unit of that thing. Like I have the same number of fingers held up as the balls, right? So there's fingers many. The other way, which is a little bit more interesting, is to use numerals. 1, 2, 3. You notice I'm erasing the ones that we've passed because you don't have to hold them. 4. The definition of 4 is the number after 3. The definition of 3 is the number after 2. The definition of 2 is the number after 1. What does that imply? 4 entails the sequence 1, 2, 3, 4. 4 is the 4th number. And when we say there are 4 balls there, we're saying there are as many balls as the symbols, the numerals, 1, 2, 3, 4. The standard of measurement for all groups of 4 is 1, 2, 3, 4. 1, 2, 3, 4 has as many symbols in it as any quartet of things that you are dealing with and measuring. So the standard of measurement is something we all carry around in our heads, which is the memorized number series. And what I did was called counting. It's surprisingly hard to define counting in a way that is crow-friendly, and I hope I got close to that. Counting is a process of measuring the quantity of items in a specified group by pairing a selected item with the number for unit 1 in our language and proceeding in strict order through the successive numbers until no item is unpaired. You got that? Sometimes called a one-to-one matching of a number and a thing being counted. So 1, 2, 3, 4, you say them or you think them. And you match with a numeral to each of the items. You have to start somewhere. It doesn't matter where, it turns out, which is an empirical discovery in a field that sense perception is supposed to be borrowed from. Albert Einstein said it's independent of experience. Well, you learn. If I count backwards or forwards or from the middle to both sides, it's still the same answer. The last number, which is 4 in our example, integrates into one mental unit all the symbols preceding it. And this is the crow-beating power of numbers. You only have to hold one mental unit. That's why I erased the preceding ones, because the whole genius of numbers is that you don't have to hold 1, 2, 3, 4. You know that 4 is a number after 3. Nobody said, oh, really? The number after 3? I thought it was the number after 18. You know that. You've got that automatized, unless Alan Salmieri is in the audience. He may not have reached that stage yet, but he will. What does all this presuppose? You have no way of knowing where I'm going with that question. So, sense perception. Because we used, first of all, the concept unit. And a unit is an existent regarded as a separate member of 2 or more similar members. 2 or more, oh, really? So before I can really get the idea of 1, I have to have the idea of more than 1. Now here's something you've never heard before in your life from Ayn Rand. Alan Gotthelf told me, well, it's from me, from Alan Gotthelf, who said he heard it from Ayn Rand, and I believed him. 1 is an object of perception considered apart, which I think is a brilliant thought, but it's an object of perception. I'm going to show you an example of this, of one or unit. Unit's the more technical. There's one. The arrow's pointing to it. The green one. Hey, there's one. The fountainhead in a bookcase filled with books. I'm pointing at what I'm seeing, not at what you're seeing. There's a screen in front here. That's why I'm pointing there. So perception gives you one versus more than one. One versus many. And if you didn't have that, you couldn't get the idea of quantity, of unit, of one, of measurement, of counting, of matching. It all starts with isolating one finger from the rest of them, or something of that order. One fork from the pile of forks on the table. But you also need perception of the numerals. How are you going to say 1, 2, 3, 4 if you're deaf and dumb? Or if you write them and you're blind? You need perception of the numerals. In fact, indirectly, you need perception of everything you learn about the world to be able to start thinking and using language and know what a symbol is. All the stuff that a kid learns from 0 to the time he starts counting. 2, 3, age. But that's not the way modern mathematicians do it. Here's how it's done according to set theory. We start with nothing, of course, because nothing is the great something that we all worship. So the empty set we define as 0. Then the set of the empty set has only one member, namely nothing. So that's 1. And then the set that contains the empty set and 1, we call that 2. This is the new math. This is Bertrand Russell's Principia Mathematica, devoted to deriving math from logic without sense perception. Yeah, it's kind of surprising that this would apply to the physical world, because this is floating abstraction. This is not grounded in perception of reality. It starts with the concept of nothing. There's only one problem. There is no concept of nothing. There is no concept of non-existence. There is a concept of the absence of a defined set of things, a defined collection of things. So if you're thinking of, well, no numbers are in that, that's okay. But still, to start with the null set, or the empty set is actually what it's called, is a tremendous inversion in and of itself. But the whole thing is a stolen concept. You have to have the difference between one and many before you can get the idea of a set. So those braces on the left, the set, are meaningless if you don't already know the difference between one and more than one. And in fact, a whole lot of other things, which is why the new math actually, I think, has now been withdrawn from the educational system because there's tremendous fail. Kids cannot learn actual mathematics that way. Okay, now we're up to measuring magnitude. Measuring magnitude means counting intervals. My whole approach to the philosophy of mathematics is really about magnitude. That's where all the problems come about. And the concept of an interval is essential to understanding how to measure the continuous. So here's a continuous line. And I've divided it into 6 divisions, 6 intervals. Except that there's a problem, but you can, before we get to the problem, you can see that, oh, now I've got an idea of how long the line is. It's 6 of those units. Maybe they're inches, maybe they're just units I made up, but I took a length to measure, a little length to measure the big length. A concretely specified unit is the standard of measuring it. Pretty obvious. Now, the problem is with that leftover stuff. What's that about? And there was a question in the workshops on introduction to objectivist, the workshops on the introduction to objectivist epistemology, which formed the appendix to ITOE as published. And there was a question where somebody said, what do you do about the fact that reality is continuous, but our mathematics is discrete, so that we always have some little bit left over, or we might? And the example, which is the chestnut in this field, is the hypotenuse of a right angle isosceles triangle. Both sides are 1 inch. The hypotenuse will be the square root of 2 inches. The problem is there is no square root of 2. There's no number which, when multiplied by itself, will give 2. There's a number that will give 4, but there's no number which multiplied by itself will give 2. And the Greeks were aware of this. And they described this square root of 2 as a non-ratio number, because the way that they could measure things was either in whole numbers or fractions. And fractions are ratios, but there was no whole number, or even if you added a series of fractions. So you say, well, it's a little more, it's 5 and a third, but no, it's a little more than a third. It's 5 and a third plus a seventh. With the square root of 2, when you actually would be doing 1 plus a series of fractions, there are no series of fractions that can express it, and the Greeks proved that. I don't know if it was Pythagoras who proved it, but it was proved by the Greeks. So here we have a problem. The law of identity says that the hypotenuse has to have some specific length, but we can't capture that length. We can't get it exactly, right? We can approximate it, but we can't get it exactly. Now, I'm going to discuss that at some length, but let me begin with a quote from Ayn Rand. Isn't there a very simple solution to the problem of accuracy? You can always be absolutely precise simply by saying its length is so-and-so. That I wrote that in because what she actually said, by saying no less than 1 millimeter and no more than 2 millimeters. But what she obviously meant in the context was its length is so-and-so plus no less than 1 millimeter and no more than 2 millimeters. Now, this is incredible, oh, sure, yeah. This is like existence is identity. Yeah, okay. Or consciousness is identification. All right, sure, yeah, I always knew that kinda. I was going to say that myself, but I didn't get around to it. You can always be absolutely precise simply by specifying the possible range that it comes in, by specifying an interval. So the length of my example is the length between 5 and 6 of these intervals. And that's absolutely precise. That's exact. Well, precision is contextual, not Platonic. We could make up finer divisions. We could do 1/16 of an inch, 100ths of a millimeter, if we had the apparatus to to do it, but it will always be measured by some human standard, by some human apparatus, and that will always give an interval. It will never give a point. Points are not things that have no parts. If you're going to use the word point in that way to mean something of zero size, there are no points. There's only intervals for the continuous magnitudes. So there's a minimum interval for any measurement. It varies with context. I used to call it I with 2 dots over it, but then I thought, the cent. So you need a symbol, and one that's on a keyboard, right? The cent sign is really what I mean, because you can calculate money, and they sometimes do. You're owed $32.52.495, but they can only pay you 52 or 53. So the cent is the minimum amount of dollars, of money, in the American system at present. Of course, we have a shrinking cent. I didn't think of that. That's a problem. Okay. So there's a minimum interval for any means of measurement. And anything below that is nil. I used to use the word nil, N-I-L, like it's used in common parlance, until I found that, at least in some usages, it means zero. And what I mean by nil is negligible. Now, I've got this symbol for it. It's a zero with an approximation sign above it. It's a round zero. It's what is negligible but not non-existent. Negligible but not non-existent. So the length in my example is 5 plus nil. Now, often it would be plus or minus, but the way I drew this, I don't see how it could be below 5. It's pretty clearly above 5. But if you've got some fine measurement, you may not be sure. Is it at 5, just before 5, or just after 5? If you've got, something so small you can't see it, or your instruments can't register it that finely, it'll be plus or minus nil. So with nil and with the perception as the base principle, I call it the primacy of perception over concepts. With that principle, we can redo Euclid, starting at the other end. Why don't we start with perceptual reality? They're things. Here's one. You're another. They're things. They have size. In geometry, we call it volume. So my first definition is a volume is an entity's extent in 3 dimensions: length, breadth, and depth. A surface is a volume of nil depth. It's got depth. So you got, the planes that you study in plane geometry. It's got a little depth, but it's negligible. So it doesn't enter into any of the calculations or theorems. It's nil. A line is a surface of nil breadth. A line has breadth. You couldn't see it if it's a drawn line, if it didn't have breadth. And if it really had, breadthless length, it wouldn't exist. So looking at it as it's got a negligible breadth is very helpful and rescues mathematics from fantasy, from mathematics land or Plato's world of forms. Now, in common usage, nil, well, let's go all the way. A point is a line of nil length. It's got length. It's got breadth. It's got depth. You make a dot of ink on your page, it's got all those things. It's got little thickness. That's the depth part, and the little size. If it didn't, it wouldn't exist. But it's negligible. Now, in common usage outside mathematics, negligible may mean, yeah, I see it quite clearly, but I don't care about it. Like you say, we're meeting for breakfast at 8:30. And you come in at 7:59 and 8:29 and 59 seconds, or you come in at 8:30 and 12 seconds, or 8:30 and 42 seconds. It doesn't make any difference. You can tell the difference between the seconds, but you don't care. So it may mean in practical daily living that which is detectable but of no importance for your purpose. But in mathematics, it really means one that is not detectable, given your present means of measurement. Only in mathematics, we abstract from your present means of measurement, and we say, given some but any means of measurement, this is below that means of measurement, whatever it may be. Let me go back before we get to that. I'm feeling tugging at me the hypotenuse of the right-angled triangle. Mathematics deals with things at any scale. If you take that line that I drew before I put the intervals on it, it could be 6 inches, it could be 6 light years. The math would look exactly the same. A light year is 6 trillion miles. I mean, not even, but it's a little over 6 trillion miles. So 6 light years is 36 trillion miles, but it doesn't make any difference. Or it might be 6 nanometers, 10 to the minus 9th meters. It doesn't make any difference. The arrangement of things are the same. So math scales. It scales up, it scales down. It doesn't make any difference. But reality doesn't. Reality doesn't scale. When you take your right-angled triangle and zoom in on it, there's no longer an edge there. At first, it gets, rough, no matter how it's been created. If it's a real triangle, at first you start to see irregularities, and that's something that Plato's making hay about when he says nothing in this world is perfect. But then we know that if you go further, you've got atoms and electrons, and they're moving around. So what does it mean to say, oh, well, the hypotenuse really has a specific identity. It's got to have a specific identity. No matter how many decimal places we carry it out, we can't capture that specific identity. Math scales. Reality doesn't. Reality changes at a different scale. The subatomic realm is not like the macroscopic realm. So the idea of a right-angled triangle, I'm not sure it has any meaning on the subatomic scale. It certainly is not subject to the kind of thinking that we do with a macroscopic triangle. So it's not like there are some things out there in the world that the mind is barred from getting to because they have an infinite identity and we have finite minds. or anything of the kind. It's just context dropping to say, well, if you have a right-angled triangle, and if the side is 1, oh, really? On what scale? In what context? You mean 1 to 18,000 decimal points? That can't be. There is no side any longer at that scale. You've got a whirling collection of electron clouds. If I may digress for a second, that's part of my answer to Zeno. You know, he says you can't cross the room because before you can go all the way, you have to go half the way, and before you can go the rest of the way, you have to go half of that. And before you can go the rest of the way, you have to go half of that. Before you go the rest of the way, you have to go half of that, and then half of that, and then half of that, and then half of that. So you never get there. But that's wrong. You do get there because your nose, on a small enough level, when you get close enough, your nose, which I assume is the furthest projection of you, if you're like me anyway. So your nose is a whirling collection of particles, and the wall is a whirling collection of moving particles, bulging in and out like this. That's what heat is, the vibration of molecules. And your nose is vibrating on the atomic scale, and the wall is vibrating on the atomic scale. If that isn't enough, what does touching mean on that scale? You know, naively you think, well, touching means the furthest out atom in your nose touches the furthest out atom in the wall, maybe. Maybe, I mean, who's to say? Atoms don't touch. You may not realize that, but electrons do not contact, electrons outside them do not contact each other. When you push one thing into another, all that happens is you get close enough so that the force that you can apply to bring the negative charges closer together is less than the binding force among the parts of the surface, so you're stopped. If that binding force is less, like you're pushing into butter, you go through and it parts. But at no point did electrons from you touch electrons from the object in question. So you see, it's a total physical ignorance. Let us put it that way nicely, because Zeno lived a long time ago. And you can't talk about the getting at the 18,000th decimal place, getting to the wall or not getting to the wall. You can't talk about, well, it's got a hypotenuse, it's got a specific length at that scale. No, it's moving around. You don't even know where the end is, and things are happening. So if you take a perception-based approach, and you look at measurement as the goal and be-all of mathematics, inferring some measurements from other measurements, you don't get into these conundrums about, well, gee, how can there be something of zero length and yet there are points? And what about the number line? What about the real numbers? I don't think there are any real numbers. I don't think there is any number line. I don't think the number line makes sense. Okay, maybe it's valid as a device, but don't reify it. It's not like there is a real number line composed of points, and for any 2 points, there's another point in between, and this creates the need for a Dedekind cut and all that sort of thing. Reality is the standard, not what is intellectually satisfying or elegant. Because I know the temptation, you know, I've been there. I've been a Platonist in my early years when I wasn't chosen for the baseball teams, when they chose teams. I retreated into the world of pure intellect And I know it's great to say, oh, the set of the null set, the set of the empty set, then the set of the set. I know the intellectual joy of manipulating that stuff. But that's not realistic. That's not right. Mathematics has to live up to reality, not the other way around. And that's my basic message, is that mathematics has to live up to reality, not the other way around. It's a means of dealing with reality, of measuring reality, or of computing the relationship between some measurements and others, going from the known to the unknown. So the way I put it is math models reality. Math models reality. Plato's way of thinking of it is reality doesn't live up to math. Reality is a model, perceptual reality. The concretes of this world are models of the forms. Reality models math. He had, in the myth, in the Timaeus, the myth of the demigod shapes out of space. He shapes the objects, and that's how the world is created. Out of nothingness, space, he shapes the things that we now see, tables and chairs, well, not man-made things, but stones and fish and men and so forth. So we are, but he doesn't do it exactly because space is recalcitrant, matter is recalcitrant. So in his view, we are models of something better. But that's not right. There isn't anything better than reality. It's math. I hesitate to say approximation, that math approximates reality. That, I think, is downgrades math. But it makes a model of reality. And my summary conclusion for all of this is in the following final slide. Mathematics, almost as good as the real thing. Now look at the inversion that I've reinverted here. I've got an apple, which is approximately round. And then I've got, on the left of it, I've got what's supposed to be the mathematical perfect circle. It's got the formula inside, x squared plus y squared equals r squared. Maybe you were taught the locus of points equidistant from a given point. That's a simplification of the apple. The apple is the thing. The apple is what it's all about. We're trying to understand the apple. Because we have a crow, we have a limited capacity, we have to simplify things. And so we come up with a circle. It's not really a circle. Plato would say, yeah, that's what's wrong with apples. They're not perfect circles. No, it's a shortcoming of the circle, or a limitation that we accept because it's better than nothing. It's better than modeling it with a triangle. And we learn the real genius in mathematics is when we learn how to iterate a process of approximation. So from the circle, we go to the ellipse, and then we shape the ellipse a little bit, and then we add in another factor. We make it a circle on top, and I guess it would be the other way, more a circle on the bottom and an ellipse on top. We get closer and closer to a I don't know, it sounds Platonist. We get a better and better model of reality as we take into account reiterating the process. And this is what calculus is about. I'm not going to go into that, but calculus is about the fact that you can improve your approximations without limit. Except you can't do it without actual limit. You can only do it without calculational limit, because there are all kinds of extrinsic limits to repeating a process, like taking half of the half of the half. One is the one I said, the physical limit on what does it mean anymore. It no longer reflects at a certain scale anything out there in reality. But the other is the limit of your cognitive equipment and the things in reality you can use to write down the numbers you're talking about. So, for example, there's a term Google, which is 10 to the 100th power. It's a 1 with 100 zeros after it. That's a very big number. I don't think there's anything in the universe that's that big. Sure, you can count combinations and permutations among things, but where are you going to write it down? They're not 10 to the 100th things to mark. There are not that many electrons, they think, in the universe. But then they came up with the Googleplex. Googleplex is 10 to the Google. So it's 10 to the 10 to the 100th. So it's a 1 with a Google of zeros following it. And that is completely unmoored from reality. There's no way the human mind can deal with that as a number. I'm going to answer objection to that in a second. And there's nothing for it to refer to in reality. There's no way that the human mind can deal with it as a number, but didn't you just deal with it as a number? Yeah, no, I mean it's a real number, like if you say 100, you can say 101, 102, 103, 104. Can you say a Googleplex and 1, a Googleplex and 2, and actually fill in all those zeros to have a number that has a Googleplex of digits? No. You couldn't know that you got it right. You couldn't write it down. Your brain wouldn't be able to deal with it. No computer could remotely come close to dealing with it. No computer ever invented because, as I say, there are not that many particles in the universe. There's not a Googleeth of that many particles in the universe. So it's a completely made-up thing. It's not a number. There was another point that I wanted to make, but it has slipped my mind, and I want to leave the time for the question period because I'm sure there'll be a lot of challenges. So if I stop here, we will have a half an hour for the question period, which is what is desirable. So I'm stopping here. Thank you very much. All right. Shay?
Yes. So you, in sort of dismissing the role of description in mathematics, that mathematics isn't descriptive, you said, yes, we can say that this ratio exists between the sides of the triangle, but who would care about that if not for the need for this inferential measurement process? How do you differentiate that from any other science? Isn't the only reason we care about any description so that we can do things from that? What differentiates?
No. Physics, the goal of physics is not engineering. The goal of physics is to understand the nature of the physical world. The goal is knowledge, not action. Now, engineering is the application of that, and we wouldn't want the knowledge if it weren't for engineering. But the goal of physics is not action. The goal is understanding. But the goal of mathematics, in my view, is to compute, to calculate, to get to know the measurements. So applied mathematics is mathematics. And theoretical mathematics is kind of meta-mathematics in a way.
So what would you say to somebody who said, no, I think the goal, or my goal as a mathematician is to describe these quantitative relationships, and I'm glad that people can apply it for measurement, but is he wrong about what he's...
No, that's Ari as a personal goal. As a personal goal, but the goal of the field, that would be like suppose you would take the contrary. You say a physicist says, my goal is to discover useful knowledge, and I'm not going to go after anything if I don't see a practical application of it right away. That would be a fine personal choice, but physics still is about theoretically understanding, gaining knowledge about the matter and how it changes, how it acts on other matter. But a mathematician can legitimately be interested in developing the tools more and the relation of the tools to each other. But what he's working on is tools, and the purpose of the field is tools. It's a tool-making thing. It's not I mean, why would you want to know about quantity? Oh, I'm studying quantity. That's the way they used to define it in the 19th century, the science of quantity. And it sounds good, but you think, why do you want to know about quantity?
Why do you want to know about stars?
Because that's the universe we live in. I don't know quite how to answer that. It's the universe that we live in. There are applications of it, but it seems to me, like quantity. Suppose you said, I want to know about relationships. Some things can be behind other things. That's interesting. And other things can be older than other things. I'm studying relationships. Is a science? That's not a science. And the science of quantity is not a science, and that's not the way it came about. It came about, whereas physics didn't come about from engineering or from, people were doing practical things, but the physicoi in ancient Greece were interested in the nature of the universe. But the mathematicians began as applied, and the theory came to explain the applied. At least that's how I'm going to play it for now.
Thank you.
Okay? Yeah.
Hiya. I'm curious how you think about the concept of infinity, especially the distinction between countable and uncountable infinity. In the theory of complexity in computer science, I think countable infinity sometimes is used for, describing certain types of problems which are not practical to solve.
Yeah. I'm glad you mentioned that, because that's one of the two things I neglected to cover. See, I lost a bunch of slides when files got overwritten, so I have to do some of this from memory. Infinity means that which can be expanded. And what I wanted to read to you, but I lost the slide, is Ayn Rand's quote in chapter 2 about infinity, in chapter 2 of ITOE, where she said, infinity, the actual infinity does not exist. And a lot of people agree with that, although Cantor doesn't. But what it means is that you can add as many units as are needed, which I thought is a brilliant way of looking at it. If there is a need for another number coming from reality, you can add another number. But it's not like there are an infinite number of numbers. There are only the numbers that's in somebody's mind. Here's a big difference between my conception and just about anybody else's. Numbers are concepts, and so suppose I said, how many concepts are there? You would say, what do you mean? In whose mind? I mean, let's take words as the shorthand. How many words are there? Well, in English, in the dictionary, there are 100,000. How many do you know? 20,000. Okay. It's the same with numbers. in some posts on HBO, I've written down numbers that have never existed before. All you have to do, I can do one verbally here. 666-591278421000003. Another 059276. That has never existed before. It's a new number. I say that based on the laws of probability. And if you think that has been said before, iterate that 16 times. That's never been said before. No computer has probably ever did. But anyway, computers don't have numbers. They have currents. That's another subject. So infinity, I think it was Pat Corvini who said, infinity is open-endedness. And I go further and I say, I do not use the concept infinity. I think its origin is in mysticism. I do not use the word. I do not use the word infinity. I say numbers are open-ended. Numbers can be expanded with no mathematical limit, but they can't be expanded beyond practical limits for practical reasons. But mathematically, you can expand them as much as you need to. So countable and uncountable infinity, I am skeptical of. People who know more math than me claim it is valid. You would have to translate that into two forms of open-endedness. And I know somebody said, you can do that. You can talk about the uncountable, like the real numbers, which is something I don't really accept. The real numbers are not countably infinite. The regular numbers are infinite, which is impossible, contradictory, but let's take it for the minute. The real numbers have numbers in between the numbers, so you can't index them. You see, to be countably infinite really means it's open-ended, but you can always see where you are. You can always, the next number is always the last number plus 1 as you expand the numbers. But the real numbers, the number line, you know, you can be adding 1, and then you have to add within that the subdivision. But there's subdivisions within that, so you can't index your incrementing of the real numbers. But I don't think there are any real numbers. They're intervals. You can define an interval, and until you've defined it, it doesn't exist. So I think Cantor was a big mistake. I don't like Cantor, but I'm a little handicapped because there are people who know a lot more math than me who say either, no, it's right, or no, it's wrong, but you can translate it into something that's right. And I'm much more sympathetic to that other thing. But for us, for the layman, what they call infinity is just open-endedness, expandability by an iterable process. It's like a loop you go through, and you can continue to go through it without mathematical limitation. But there will be practical limitations. Okay, so I don't know if that's a satisfactory answer, but that's my view. Yeah.
Does the corruption of math spill over to other sciences, subjects, which I would assume? If so, could you name one or two most?
No, they've got their own corruptions. I don't think that mathematics has spilled over to corrupt other sciences, but I could be naive.
Maybe physics, at least. There's some impact on physics, some bad things in physics or outside physics or whatever.
No, the bad things in physics came from the bad philosophy of the quantum people. And I think mistake of Einstein, I'm not sure. I think Einstein was onto something. Let me bring this in. Okay, here's a wild new thought. if you say there is no infinity and the concept is worthless, people will rightly ask you, well, hasn't there been an infinite amount of time in the universe? And that got me thinking about, well, let me answer that first. Has been since when? Amount of time is between some time and some time. So however far you go back, that's a finite amount of time. So the presumption is, well, we've got all of time here, and look how big it is. It's infinite. We don't have all of time. That concept doesn't mean anything. And that got me thinking about what is time, and I have a new theory of that. Ordinarily, Aristotelians and objectivists admire Aristotelians, so objectivists too say that time is a measure of motion. But I don't think that quite captures it. So I have a pendulum going this way. And I say, while the pendulum went this way and this way, I walked across the room and took 3 pendulum swings. And that's time. Well, that's a measurement, yeah, of your motion. But when I said, my car is from 1960. I have a car that's from 1960. That's not hypothetical. And that was a time, a more innocent time. Think about 1960. That's not about some one clock and some one manufacturer of a car or something like that. Time refers to the simultaneous occurrence of all the motions in the universe, except Einstein showed it couldn't be all the motions in the universe, and Ayn Rand also held that. She said time was local, meaning restricted to our galaxy or some, it did not embrace the whole universe. By local, she didn't mean South Florida. She meant astronomically, it's limited locally to some galactic scale. And physicists talk about the light cone, how far light can go. And Einstein raised the question, what is simultaneous? What is simultaneity? I'm not sure he gave the right answer to that, but that is the crucial question, because I think time is the system, the ensemble, the system of things changing at the same time. Simultaneously, whatever that means. So the root thing to go for is simultaneity, not one motion against another motion, but one motion against all the motions in the universe. So I think that's the right question to ask. What is it to be simultaneous? And are things happening here simultaneous with things happening at a star 4 light years away? Or 4 million light years away? What does at the same time mean when what we're now seeing while we're doing something here is an event, say a nova, that occurred maybe 100 million years ago? I don't have an answer to that, but I think that is the question of the physics that leads to relativity theory, and maybe it can be reconceptualized. There was another aspect to that question. But it's gone with the mists of time, yeah.
We have a question from the live stream. What is your perspective on imaginary numbers? Would you say they don't exist?
I'm glad that was asked, because that's the other thing I left out. I don't think any numbers exist. Numbers are mental tools for measuring. Imaginary numbers do that job. Imaginary numbers, as I understand it, refer to a rotation. And they're useful for a rotation of less than 180 degrees. See, for negative numbers, it's 100, this Ray Schramm explained to me. You're adding more and more, or let's say I'm walking this way, and now I'm at a velocity of 1 mile an hour, and now I'm going to go minus 1 mile an hour. That would be backwards 180 degrees. But what if I'm going this way? Negative numbers can't handle the fact that I've turned in a 90-degree direction. But imaginary numbers do that work. So here's my new, this is the other slide that is missing. I used to attack various numbers, poor numbers. I used to say that numbers are counters, and when I'm talking about long ago, as long ago as day before yesterday, I used to say that numbers were counters, and if you can't count with them, they're not numbers. So I said the irrational numbers, like the square root of 2 is not a number. Pi is not a number. Even the square root of 4 is not a number because it's an expression, not a number. Now I've reached a happy compromise where I think the point is not to decide how far we're going to expand the concept number. The point is to get clear on the hierarchy. 1, 2, 3, 4, 5 are the basic numbers. They are the hierarchical root of anything more advanced. On that base, you can define minus 1, 2, 3, 4. Even children get this. The Yankees are 3 runs behind. Now they're 2 runs behind. Now they're 0 runs behind. They're even. So the negative numbers in 0 are relative. They're a relationship to something taken, in this case, the other team's runs, taken as the starting point. So they are not primaries, but they're quite legitimate, of course, and fractions. Fractions you can count with, so I was willing to accept that. And Ayn Rand names them as numbers. So you can say 1/5, 2/5, 3/5, 4/5. You've simply taken a different unit. Just as if you count by 5s, 5, 10, 15, 20, it's not that you've gone into some other realm, you're counting by 5s. And if you count by 5ths, that's obviously based upon understanding the 1, 2, 3, 4, 5 basic natural numbers, they're sometimes called. And the irrationals are built upon the ratios. They're built upon the fractions, successions of fractions added on to the numbers. So they are, I'm not never questioned their legitimacy, but I used to say they're not numbers, they're numerands, made-up words. But it occurred to me, I'm not exactly sure what, you can do things with irrational numbers like the square root of 2 that you do with regular numbers. Add them, subtract them, multiply them, divide them. And if you square them, they become a regular number. So I'm not going to legislate, where can you extend the concept number 2, but I do say that the base, the primary, out of which all the rest is built, are the natural numbers 1, 2, 3, not even 0, 1, 2, 3, 4, 5, etc. So the question was about imaginary numbers. If they are a good tool and they accomplish something, they are valid. Whether they're to be called numbers or numerands is secondary to what are their hierarchical roots? To what do they reduce in perceptual reality? See, one reduces to this as opposed to this. And other things like the real numbers, I don't think you can reduce to perceptual reality, but I'm open to persuasion.
Yes, I was hoping you could say a bit more about how to think about nothing, given that it's not a concept, as you put it.
Well, there's two different things. There's zero, which is a relative nothing. It's the absence of what has been and could be again. Like I have zero cash in my account, but I could have money in it, and I used to have money in it, and I hope to have money in it again. But non-existence, the total zero, as Ayn Rand sometimes called it, there not only is it non-existent, that's a corollary of existence exists, non-existence non-exists. But there's no concept. And I asked her that in the workshops, is there a concept non-existence? And she said, in the absolute sense of the total void with nothing to follow it, no, it's not. In the same, she said, if you're saying non-existence like you're saying existence, the totality, there is no non-existence and no concept non-existence. Now that raises the interesting question of incidentally, it was Parmenides who said that. What is not cannot be and cannot be thought. And he was absolutely right. And the next one, I'm going to give a credit to Plato. If non-existence is non-existing and there's not even any concept, what are we saying when we say not? Right? I'm not in Kansas City. Plato answered that. He said, it's other than, it's different from. I'm in some place, and that place is different from Kansas City. I haven't said what place I'm in yet. Turns out to be Miami, but I'm not, that's a different place. I'm in a different place from Kansas City. And all negations are differences from. They're not nothingnesses put in there into the middle of being, or even on the side of being. Okay?
Thank you.
Yeah.
Thanks a lot, Dr. Binswanger, for a very interesting lecture. I wanted to ask something regarding the relation of modeling that came up in the slides several times. When I think of physics and the role of mathematics in physics, sometimes it seems to me that the best way of thinking about how mathematics models things is by parallelism. So, for example, if I have an equation, then I can say, well, the right hand side describes the cause, for example, force. And the left-hand side describes acceleration, which is the effect. And so I can read causality in the equation. But sometimes a different relation appears to be the case, which is that mathematics simply adds quantitative information about a physical process or entity. So there is an adverbial kind of function and the parallel kind of function. I'm not sure which one is correct.
That's too deep a question for me to know the answer to, having never considered it, but you're absolutely right. And some equations, see, I guess it goes back to this, that math is a calculative tool. The fact that we express laws of nature in mathematical form, you cannot read off from that the causality involved. For instance, you cited F equals MA, but you also work with M equals F over A and A equals F over M. So you deal with non-causal versions of it. And that's perfectly all right, because you're computing knowns, unknowns from knowns. You're not describing. But I think when you state the laws of nature, if you know the causality, you should do it in that order. And I guess in that case, it's A equals F over M is the statement of causality. The acceleration of body experiences is caused by the force applied to its mass. So that would strangely be the canonical form, not F equals MA, which is mathematically simpler because it doesn't have a division. But that's a good, deep question. I wanted to say what happens when you go out infinitely far, but go ahead.
Thank you for the talk, Dr. Binswanger. My question relates, I have often heard, particularly from students of the empirical sciences, that that math and well, I call math to be a science, and in a sense, because of the method of binding it to perceptual reality that you explained. But these students do not think of math as something that is connected to the real world, but instead as some abstraction that, yeah, you can make empirical experiments with numbers and you can learn some information from them, but these numbers really don't mean anything. Could you explain how, how does your approach of binding perception to mathematics would answer that claim?
Well, if they can't, their terms are not reducible to perceptual reality, then they have no content. Then they're just sounds. How did they give them meaning? And of course, there's the formalists in mathematics say they don't have any meaning. They're just like chess moves, in which case they have no function. And that's what, Gödel, who's both a friend and an enemy, because Gödel's theorem was aimed at these formalists. It's called on the formal undecidability of something, propositions within Principia Mathematica. It's on the formal undecidability. I forget the rest of the wording. And he showed that if you take mathematics to be without meaning, but just like moving chess pieces around, you can create a pattern of symbols that is a well-formed formula, as they call it, in that structure, which cannot be answered as to whether it is valid or invalid, provable or unprovable, actually. And it's the symbols that amount to, this statement is unprovable by Principia Mathematica. So, I mean, that was good, but what is not good is the interpretation, at least, well, he was a Platonist, and he was attacking the formalists from the standpoint of, look, mathematics really talks about these ideals that exist in another realm. And that's not good. And the public media presentation of Gödel is, well, he refuted reason. And that he refuted Bertrand Russell. And Bertrand Russell and reason are very different things. Never the twain shall meet. That was the last question. In 40 seconds, what happens if you go out for an infinite amount of time? Well, I could say, tell me when you get there. But there's no meaning to out. This is like what happens when you take half of half of half and you're crossing the room. The scale comes in and there's no longer any definite positions to be talking about. And the same thing goes for if you go out for an infinite amount of time even a finite amount of time in a spaceship. Out from what? You go out long enough, the Earth doesn't exist anymore. Where you took off from, of course, it's moving. So it's out from what? How do you define out? There's no meaning to out on a scale where you cannot get your bearings from the earlier time. There's no longer any sun. There's no everything is dissolved into particles in the ultimate heat death of the universe. So the question is wrong. There's no such question. It's like, how would we know if everything in the universe doubled in size overnight while we were sleeping? So even the rulers doubled and everything doubled. There's no meaning to everything doubled. You have to double in relation to something. There's no meaning to going out forever. Out has no meaning then. Thank you very much.